But do I speak enough loudly? I don't. This is already.
Oh yeah, this is the new. Yeah, that's the new.
But I'm.
You start talking. Good afternoon. Just to have it here. Hello.
I'm sorry, I'm not sure about acoustic. But should I speak loudly because I'm not sure about the acoustic?
Pues muy buenas tardes a todos. Hoy tenemos el gusto de escuchar la plática del profesor Arkady Leiderman de la Universidad Ben-Gurión ahí en Israel. Pues él es experto conocido en el área de grupos topológicos, pues espacios de funciones relacionados con análisis funcional. Bienvenido a Arkady. Él va a hablar, pues aquí está su título. Entonces, espacios localmente convexos libres, CX y nucleares también. Pues adelante, Arkady, you are welcome. Go ahead, please.
Thank you. Okay, I will try to speak loudly because I'm not sure that you hear me well. It's okay. And of course, thanks for inviting me. Only due to the support of Professor Antonian, I came to Mexico because it's not easy this time to come from another continent to Mexico. And maybe we also will meet in Puebla conference. Okay, as you see, the title is about stuff which is related both to functional analysis and general topology. I will try to explain all notions. I don't know about the time, maybe some small pieces of the proofs I will try to provide. But first of all, let me say that this is actually a paper which has been already published. It is a joint work with Professor Uspenskij from United States. And this paper with the same title is published in Mediterranean Journal of Mathematics. So you should not be in a rush. If you don't understand something, you can find all details in this paper. Okay, now, first of all, what is the main object of my research? It is a so-called free locally convex space. By the way, I'm here not for the first time. I remember that I gave a talk, not in this classroom, but in another room. It was in 2016. So I come here each 7 years. And And the subject of my talk also was about locally convex space, but that time I talked about some other properties which are more related to geometry. It doesn't mean that I assume that you remember the content of my talk from 7 years ago, but it is the same main object, but the properties today will be more close to some functional analysis. So it's not pure topology, it's some mixture of topology, general topology, and functional analysis. Okay, so what is the definition? Definition is the following. You take any Tychonoff space. So X here is just any Tychonoff space, and you want to define a locally convex space such that X actually is a set of generators. So X is a so-called Hamel basis. It means that all elements of L of X are just formal linear combinations of points from X. This is from an algebraic point of view. From topological point of view, we wanted to have free topology. What is a free topology? You see that our requirement is that every continuous mapping, small f, from X to any locally convex space E, we wanted to extend to have a lift to a continuous linear operator F bar. So this is the official definition of a free locally convex space. And of course, from the definition, it's not clear why this object exists at all. So from algebraic point of view, this object is clear. Again, it is a set of all formal linear combinations, but topology is defined in this sense. So this is a theorem. Of course, it's not my theorem. It's a classical object that this object, a locally convex space, exists. And in fact, it is a unique. So if you want to know the history is that a prominent Russian mathematician, Markov, just mentioned that such objects should exist in one short paper. It was somewhere in 1940 something, so more than 70 years ago, but he did not provide any details, and the details of this construction were done by another Soviet mathematician, Rykov. But again, it was more than 60 years ago. Okay, sorry. Now, another object of my talk. What is nuclear locally convex space? It's not so easy to explain what is nuclear because the official definition is not so easy. But anyway, on this slide, you see what is the official definition of nuclear locally convex space. So a locally convex space E is called nuclear if any continuous linear operator from E to any Banach space is a nuclear operator. Here on this slide, you see what is the definition of nuclear operator. Okay, it's not so, how to say, easy to understand from the first point of view, but anyway, the official definition is the any operator we can write in such a form. Okay, you see what is the form, some formal linear combination, lambda here scalars. Okay, this is a sequence actually from L1. The sequence of Fn, it is a sequence of linear functionals defined on the equicontinuous, and Yn some sequence of elements from B. It's not very convenient definition. There are many other equivalent ones, but please don't worry, because actually I don't use this definition. Okay, we somehow will treat the property to be nuclear with the help of some other known results. So this is official definition, but I never use it actually. Okay, what are the properties of this class of nuclear locally convex space, and what is the history for what is invented at all? Okay, so now you see very prominent names, because actually this definition is due to Alexander Grothendieck, and the properties, everything here is due to Grothendieck. So you see that every subspace of a nuclear locally convex space is nuclear. Every Hausdorff quotient, again, nuclear. And now what is surprising, the product of any family, okay, of any cardinality of the family is again nuclear. Now there is a construction known as in the theory of locally convex spaces. It's so-called locally convex direct sum, but of only of countably many nuclear locally convex spaces. Again, nuclear. And now for me, it's important, the last one, that every nuclear locally convex space actually can be isomorphically embedded into the product of Hilbert space. What is the reason for this definition? And what is the connection to the classical Banach spaces theorem? You might think that is another generalization of Banach spaces. No, it is somehow perpendicular line of Banach spaces. Why? Because actually there are no infinite-dimensional Banach spaces which are nuclear. Banach space can be nuclear if and only if it is finite dimensional. So it is a generalization only for finite dimensional Banach spaces. And why it's so important? Because the origin of this notion actually is from the classical analysis. If you remember from your background, if you consider the space of distributions, then you first of all define so-called Schwartz space. It's a space of smooth functions on Rn such that functions themselves and their derivatives, they are rapidly decreasing. And you might remember that it's not norm space, it is some locally convex space. And this locally convex space, Schwartz, which is very important for the zero distributions, okay, in Russian terminology, this generalized functions. So these functions, this function space is nuclear, and also another example of nuclear space is the space of entire holomorphic functions of complex defined on the complex space. This is another prominent space from complex function space. Okay, so this is a background. This is the importance of this object. I mean, nuclear spaces. And now another, which is very close to this nuclear, is a so-called Schwartz spaces. Okay, now this is the famous Schwartz, which has got Fields medal. Yes, he has got Fields medal for the theory of distributions. So, but of course, not Schwartz gave the name of Schwartz in space. It's also due to Grothendieck. So Grothendieck called a locally convex space Schwartz, and here the definition is much more easy to understand. The point is the item A. This is the official definition that every continuous linear map from E to any Banach space, now it should be a compact operator. Not nuclear, but compact operator. Compact operator, you might remember from the basic course in function analysis, operator is called compact if it sends a neighborhood of 0 to a relatively compact set. I mean, to a set with a compact closure. For example, if you take identity operator from one Banach space to another Banach space, it's not compact. Because compact operator, okay, again, requires that the image of a ball is small in the sense of compactness. And the internal definition of Schwartz, here you see official equivalent formulation. It reminds in some sense compactness. So definition, characterization item B, okay, where is this? Is the following. So for every neighborhood U of 0 in locally convex space E, there is another neighborhood V of 0 such that for every scalar, my spaces are real. For any lambda, you can cover V by finitely many translates of lambda U. Okay, you see finitely many, it is because of compactness. So two definitions A and B are equivalent, But again, for my purposes, I somehow will do everything with definition A only. So this B, we use actually once, but not so important. Okay, so you have nuclear, you have Schwartz. Now, another class, okay? I just give you a general background. Multi-P locally convex space. What does it mean, multi-P? P, this is calligraphic P. Assume that you have any class calligraphic P of Banach spaces, okay? And then we say that locally convex space E is multi-P if E can be isomorphically embedded into a product of spaces from P. So the number of factors in this product can be arbitrarily large. We wanted to have E as a subspace of a big product. For instance, this is very easy observation. If you take any locally convex space with its weak topology, then it is multi-Hilbert. Why? Because every locally convex space with weak topology can be embedded into the product just of real lines. So what are the classes of Banach spaces which are interesting? You can take the class of all Hilbert space, and in this case we have multi-Hilbert spaces. We can take the class of P, class P of Banach spaces, all reflexive Banach spaces. Then you have multi-reflexive. But the main definition is, main motivation is the following. Result of Uspenskij. This is a rather known result, very elegant result of Uspenskij from 2008. He proved that for every Tychonoff space X, this object, I mean locally convex space L of X, can be isomorphically embedded into the product of Banach spaces of the form L small of gamma. What is L1? It is a space of sequences such that the sum of the components is bounded. It's convergent series, in fact. But gamma here is not countable set. Gamma here can be any set. So Lx in this language is multi-L1. L1 here is the class of all Banach spaces of the form small L of gamma. Now, instead of L1 of gamma, we want to have reflexive Banach spaces or Hilbert spaces, etc. So, okay, this is a remark that the class of Schwartz spaces, also the class of all nuclear spaces, the class of all multi-Hilbert, and the class of all multi-reflexive, they constitute a variety. What is a variety? In algebraic sense. So it is closed under the operation of subspaces, quotients, products, and is isomorphic images. So these classes of locally convex spaces behave nicely. And now, general picture. Forget about free locally convex space. In general, we have the following picture that nuclear is the strongest property. It implies L is Schwartz. What L is nuclear implies that L is multi-Hilbert. Actually, this is a result of Grothendieck. L is Schwartz implies that L is multi-reflexive. It's you just look at the proof of Grothendieck and do the same, and then you have such a result. But anyway, we can prove it again. And multi-Hilbert, of course, implies multi-reflexive. So this is a diagram, and in general, no implication can be reversed. I mean, there are examples in general, in the theory of general locally convex spaces, that these implications, they are not reversible. But our question is what can be done if we are talking not about general locally convex spaces, but about our L of X. So the subject of our research is what can be Then here, if we can assume that L is a free locally convex space. And these questions actually were posed not long ago by our friends. Vladimir Pestov asked us explicitly when is L of X multi-Hilbert, and another friend of us, Mikhail Megalishvili, asked when is L of X multi-reflexive. So these somehow are new questions. If you ask me why we did not consider these questions some 30 years ago, I don't know what to answer. Somehow these questions appeared just 2 or 3 years ago. Despite that, all definitions are known at least 50 years. So this research is new, despite we consider some classical objects. Okay. Now, first theorem. So first theorem says that actually LFX is multi-Hilbert very rarely. Okay. So the theorem says that once you know that X contains an infinite compact subset, and then LFX cannot be multi-Hilbert. We have a proof. The proof is not trivial, okay? I don't know if, okay, by the way, so I finished my talk at 2 o'clock, right? So actually I put some slides which explains what is the main idea of the proof, but the proof is not so trivial, okay? If I just wanted to somehow to impress you what is the technique that we use here, okay, so there are some stages, okay, let me do it briefly. First definition, we say that a subset C of a Banach space E is an ellipsoid. It's not a ball, but ellipsoid, if it is the image of some ball from Hilbert space H. So assume that you have a Banach space E, and some set is called ellipsoid again. If you can find some Hilbert space, some a closed ball, and then a bounded linear mapping H, such that H maps a ball to ellipsoid. From this definition, immediately it follows that the ellipsoids, they actually are weakly compact, and hence they are closed in E. Now, this is a non-trivial fact from Banach space theory, and it is says the following, that if you have a Banach space which is not Hilbert, then surprisingly you can find inside Banach space E a countable sequence, just a countable sequence, which is so big that you cannot cover it by any ellipsoid. Okay, I cannot prove it actually, but I just can tell you that there is some known results from the theory of Banach spaces, that once you have a Banach space which is not Hilbert, then you could find a sequence of finite dimensional subspaces such that they are far from being Euclidean space, so-called Banach-Mazev distance goes to infinity. This is if your Banach space is not Hilbert. This is first observation. And now, let S be a non-trivial countable convergent sequence. Then we claim that LFS cannot be multi-Hilbert. Why? No, here actually on this slide there is a proof. So what is the proof? Suppose, on the contrary, that LFS is multi-Hilbert. Again, S is just a simplest countable convergent sequence space. Now, you embed S into some non-Hilbert Banach space. So you have a lot of freedom. Here you just take your favorite non-Hilbert Banach space. Then, according to the definition of L of x, you can extend, you take a extension, a lift of f to f hat on L of s to E. And now, this is known result because you assume that L of s is nuclear, yes, is multi-Hilbert, sorry. Then you can factorize this mapping f hat. You can represent it as a composition of two other operators, p and g hat. And now g hat will be a Hilbert space. And so we are in this following situation, okay? You have such a diagram, okay? This is the diagram. S here is convergence sequence. H here Hilbert. E is a Banach space which is not Hilbert. Then you can convert this diagram to the mappings from L of x, etc. And from the commutativity of this diagram, it follows that your image, image f of s, will be a subset of some ellipsoid, which is not possible because we took f of s such that it is not contained in an ellipsoid. So this is the contradiction. This is the idea. Okay, let me continue. Now we just assume that K be any infinite compact space subset of X. Again, I want to prove that if X has some infinite compact subsets, that L of X cannot be multi-Hilbert. So again, the proof goes on the contrary. Let X has an infinite compact subset, assume that L of X is multi-Hilbert. Then we can identify L of K just a subspace, linear subspace of L of X. Then L of K itself is multi-Hilbert. And then because K is infinite compact space, you have no troubles. You just take any continuous map with infinite image. And now M is the image of pi of K. What is the advantage? Because if K is just a compact space, but why it so happened? I did something wrong, I'm sorry. Okay. Again, I started here with some abstract compact K. Look, K is not metrizable. Okay, here K is not metrizable compact space. It might happen that K does not have convergent subsequences. If K is not metrizable, there's some huge compact spaces without convergent sequence. So now, because we took some continuous mapping pi from K to 0, 1, then the image, of course, is just a subset of 0, 1, and it has convergent sequences. And from this, again, maybe I spent too much time on this, and then you can show that because of M, which is just metrizable compact, and in our machinery about the convergent sequences, we can show that we have a contradiction with the claim that L of convergent sequence is not multi-Hilbert. This is the main structure of the proof. Okay, maybe it's lack of details, but anyway, this is the main idea. Let me continue. Okay, so now we have even worse situation. What is the state of art? If X is just a K space, then L of X can be nuclear and can be multi-Hilbert if and only if X here is just a countable in discrete space. So this sounds like never L of X can be multi-Hilbert space, because if X is a space like compact or even K space, then it can happen if and only if X is countable and discrete. And to our surprise, we found a large class of X such that L of X is nuclear. So up to now, I say that L of X is very rarely nuclear. Okay, but anyway, we have a class of topological spaces such that L of X is nuclear, and they are not discrete. So this is another story. And now this is a story about some general topologies. So what are the definitions? Definitions are the following. A Tychonoff space is called projectively countable if every metrizable image under continuous map is countable. This is a known definition. Another known definition from general topology is the following. A topological space is called P space. It's not our definition. If every G delta set is open, it can happen, okay? In topological space, it can be that every G delta is open. And then there is an easy observation that every Lindelöf P space is projectively countable. And it is known that so-called omega modification of topology of any scattered Lindelöf space gives you a Lindelöf P space. Look, I use here some topological notions. If you wanted to know all definition can give you, for example, do I need to say what is scattered? That's fine. Scattered if every subset has an isolated point. And Lindelöf is a generalization of compact. If any open cover, you can find countable subcovers, then it's called Lindelöf. And now we have such a nice theorem that if X is projectively countable P space, then L of X is nuclear. This is a new and unexpected result. And you can ask me, what are the examples of projectively countable P space? There is so-called the Lindelöfication. So the example of such a space, okay, it is so-called one-point Lindelöfication of any uncountable discrete space. So it has a lot of isolated points, but one point is not isolated. And you define a neighborhood of this non-isolated point like a complements of countable sets. This is a known object from general topology. And also, we are able to find some more sophisticated examples of projectively countable P space, which are not Lindelöf. Okay, so the class of X is such that L of X is nuclear. It's not a trivial class. And by the way, we don't know a complete characterization. So this is some intriguing class. I mean, to characterize completely this class, we are not able. This is an open question. I will ask the open question at the end. So, okay, this is problem one. Let X be nuclear. Does it imply that X must be projectively countable? This is an open question. We don't know. Okay, let me continue, but I skip something because I don't have enough time. Okay, now let me tell you what do we know about Schwartz and multi-reflexive. Now, first of all, I told you in the beginning of my talk that it is a known fact. Every Schwartz L locally convex space is multi-reflexive. You can ask me why. What is the reason? And the reason is quite non-trivial because we need to use some known factorization from Banach space series. So let me give you some details. I explain you what is the proof of this known fact, why every Schwartz locally convex space is multi-reflexive. What is the definition? You remember, definition is the following. Assume that you have a continuous linear map from L to some Banach space, okay? We want to show that this mapping can be factorized through some reflexive Banach space. This is actually a main point. Because if you wanted to show that locally convex space is multi-reflexive, it means that you have the topology, the situation, the topology of L can be characterized, can be generated by all linear mapping from L just to reflexive Banach spaces. So, but you start with the map from L to some Banach space, which does not have to be reflexive. And first, you use some notion from Banach space series, so you have first factorization. You see B1. B1 here is some reflexive Banach space. Okay, and now to this diagram, you add another Banach space, which is reflexive. So in fact, we have the following sequence: from L to B2, from B2 to B1, from B1 to B. And here B1 is reflexive. Why? Because we use so-called Davis-Figel-Johnson-Pelczynski theorem. This is a very powerful tool from the theory of weakly compact operators. So the classical is actually classical theorem now. It says that every weakly compact operators between Banach spaces, it admits a factorization through reflexive spaces. Now, from these four mathematicians, Figel and Johnson, they are still alive. Johnson is, I think, 85 years old, yes. Okay, so our theorem says the following: opposite to nuclearity, we have some nice picture. So if X is a good space, what is the good? Locally compact, both, and sigma compact. So assume that X is both locally compact and sigma compact. Now, for example, if X any compact, of course, it is locally compact and sigma compact. So if you look at X, you can look at X as a compact space. So once you know that X is compact, then we have a proof that L of X is Schwartz. And then we asked ourselves what about the converse? In which situation you can say that L of X is Schwartz if and only if X is locally compact and sigma compact. It's not the case, but if you assume some extra assumptions on X, then you can have also a converse implication. Okay, so this is a theorem. This is the theorem we are proud of, that if you assume in advance that X is not just arbitrarily Tychonoff space, but assume that X is first countable and paracompact, then you have equivalence between three properties. L of X is Schwartz, it's the same as L of X is multi-reflexive, and it is the same as saying that X is both locally compact and sigma compact. In particular case, when you have first countable and paracompact, when X is metrizable. So if you start with a metrizable space, then for metrizable space, these three properties are equivalent. Let me say again. L of X is Schwartz if and only if L of X is multi-reflexive, if and only if the structure of X is the following one. It has to be both locally compact and has the countable base. So this is the most natural metrizable space like R, for example. R is locally compact and has countable base. Now, actually, every open subset of a Euclidean space is such. It is locally compact and has countable base. Okay, what about the ideas of the proof? Of course, this theorem also is not very trivial. And let me just say you a few words about some interesting feature of the proof. To prove this theorem, we use so-called countable metric fan. What is this object? Metric space which is countable, but it is not a convergent sequence. The structure of this metric fan M is a bit different. So the definition of M is the following. It is just a subset of known object which is called metric hedgehog. And formally, but for this hedgehog, you have only countable many spines. Formally, what is the definition of countable metric fan? You have countable many sequences, n times n, and you add some ideal point, let's say infinity. And then the topology on this M is the following. Every point from n times n is isolated, and the neighborhood, the basic neighborhood of this point infinity is a set of the following form. You remove only countable many elements from the first n, you remove n first element times n, and then this is the nth neighborhood of infinity. Why this object is important for us? Because it is some test for being locally compact. There is a known fact from general topology. It says that once you assume that your space is first countable para-compact, then it's not locally compact if and only if it contains a closed copy of this countable metric fan. So this is like, you know, in chemical experiments, if it contains a closed copy of M, then it's not, then it is not locally compact. So it leads you to the question, what you can say about L of M. Is it multi-reflexive or not? And then the fact 9 says it is a theorem that L of M is not multi-reflexive. Another test space which we need, it is an uncountable discrete space. So fact number 10. Let X be uncountable discrete space, and we have a proof that L of X also is not multi-reflexive. So we have some test spaces. One test is with the help of M, another test with the help of uncountable discrete space. And then we have, okay, this steps by step. So if L is multi-reflexive, then every discrete collection of non-anti-open subsets is countable. And then we have such a corollary 12. It says that if L of X is multi-reflexive, then every metrizable image of X under continuous map must be separable. This is ingredients of the proof of the main result that I formulated, that for para-compact and first countable space, 3 properties are equivalent. No, I can provide more proofs, but maybe it's not so important. Okay, let me just give you some examples. Actually, I think I skipped some details, but anyway. For example, if you like some general topology, I take now some very well-known object from general topology, it is so-called space of countable ordinals. So on this slide, you see, let X be an ordered topological space of all countable ordinals without the last point. Then what do we know about this space? This is a very classical object. We know that X is countably compact, Hence, pseudo-compact with first kernel, with locally compact, everything is okay. But X is not sigma compact. So there is no contradiction with my theorem. Why? So I claim that L of X nevertheless is Schwartz, but it's not sigma compact. Why it happened? Because X, despite of the fact that it's so good, but it's not paracompact. So once you assume that X is not paracompact, you do not have such a theorem. You can't have that X is not sigma compact, but still L of X is Schwartz. So I want to convince you that our theorem is good only for paracompact space. Once you get rid from the assumption that X is paracompact, and you have some other examples. Okay, so I have several open questions to ask you. We don't have any particular example of a Tychonoff space X such that L of X is multi-Hilbert but not nuclear. This is an open problem, number 2. Also, we don't have any particular example of a Tychonoff space X such that L of X is multi-reflexive but not Schwartz. So in our theorem, you saw only equivalence. So for metrizable X, for example, I proved you that I should explain you that L of X is multi-Hilbert and nuclear. Just the same. In general, yes. For general locally convex spaces, these classes are different, but for our particular object L of X, we don't know if they are different or not. More specific questions. Now here I use some known results from the past. This area was very popular, but not, of course, very recently. So this area of locally convex spaces, I mean, area of research was very popular in 70s, if you wanted to know. So there is some nice result, which is due to German mathematician Randke. It says the following, that every Schwartz space can be isomorphically embedded in some sufficiently high power of a specific Banach space, C0. Classical Banach space is 0. This is one known result about Schwartz spaces. But nevertheless, there are examples of Schwartz spaces. You remember, Schwartz space is multi-reflexive. But surprisingly, you can find Schwartz space which cannot be embedded into the power of Banach space, very classical, LP. LP, as you know, is a classical reflexive Banach space. So any Schwartz space can be embedded into the product of some reflexive Banach spaces, but it doesn't have to be embedded into the product of LP. And the third surprising result, which is due to Steve Saxon, it says the following, that once you take any Banach space, take any Banach space you like, then every nuclear space can be embedded into the product of these specific Banach spaces. These three classical results from the theory of Schwartz and nuclear locally convex space, this is the motivation for our question. So the questions are the following. Problem 4. Can we characterize all Tychonoff spaces X such that L of X can be embedded isomorphically in some sufficiently high power of the classical Banach space C0? So we don't know this. And also we don't know what can be a characterization of all Tychonoff spaces X such that L of X can be embedded in the product of LP for any P. This is also a nice question, in my opinion, but it is open. Thank you for your attention. Yes, I finished the earlier 5 minutes. I'm sorry.
No, I was just waiting for the light to start.
Say it again. That is my job. So, do you have any questions? Okay.
Okay, maybe if X is compact, for example, Tychonoff cube,
Hmm.
what can we say about LX?
L of X is Schwartz. For any
Okay.
Euclidean compact
Okay.
space, L of
Okay,
X is
now
Schwartz.
If X is locally compact,
Again,
X is
if
locally
X is the metrizable space,
no, not metrizable, locally compact and separable. Can we say something?
locally compact and separable, but not metrizable,
Not metrizable, yeah.
I don't know. We know only if it is somehow close to being metrizable. First countable is close to metrizable. Once we don't know first countable, no, I cannot answer.
Okay. Okay, thank you.
Any other questions? Maybe you have a question in Spanish and I can try to translate. No, that is not the case. You really don't have any questions. I noticed that in the presentation, covering properties, paracompactness, Lindelof, being compact, and all that stuff, they appear quite frequently. Is that by design? I mean, that you started thinking about covering properties and then finding
Still,
results?
we have
or-
some limitations again. It's not the situation that if I assume only paracompactness, then I can characterize when L of X is Schwartz. I need more. As I answered to Sergey, we need not just paracompactness, but something extra. Extra is first countable. So for first countable and paracompact, the picture is nice. But if you omit something, then we don't have a characterization.
Okay. Questions?
So this is open questions for young mathematicians.
Arkady, there is another notion of nuclear groups, topological
Oh,
groups.
yes,
Is
yes.
there any,
Yes,
what's
yes,
the
yes.
relationship?
Actually, if you consider a free topological abelian group as a subgroup, then if locally convex is nuclear, then free abelian group is also nuclear.
Nuclear.
Yes. So there is a parallel theorem for groups.
Okay.
I did not want to touch this subject, but in the same paper, you find a lot of information also about free abelian topological groups.
Okay, thank you.
When they are Schwartz, when they are nuclear, yes, that's true.
Any other questions or comments? No? Well, thank you very much.
Thank you.
I shouldn't be saying this, but I thought that I wasn't going to enjoy your talk, but it was a very enjoyable talk. Thank you.
Thank you.